Okay, so I hope you enjoyed the group theory the last time. And today we will cover the general case of solving linear equations, which will lead us to vector subspaces and ultimately to the four fundamental subspaces of a matrix, which will give you a complete picture about what to do if you are facing a system of linear equations which does not have a square matrix, which have either more equations that are not more or that's a different number of equations than unknowns in general. So far we only covered the square system, the square case, and we will see what needs to be done in order to generalize it to absolutely arbitrary case ax equals b, where a can be any dimension. So I saw that the most of you figured out how to do the spline stuff. Some of you even figured out how to do the not to not extra credit constraint, so that's great. I haven't decided completely yet, but I think there's the fall break, and I think I might just not do any project or homework to have you appreciate the break a little bit better. Lots of you are going away anyway, so I'll see about that when we prepare for the Wednesday class. All right, so shall we jump into this? So the topic today, and probably next time as well, are general linear systems. So as I said, the number of equations does not have to be equal to the number of unknowns, right? As you can see, even in the simpler square case, if you recollect what we were talking about it before, remember that led to LU decomposition and so on. Even in that simple case, there were some special cases, right? Remember, the solution didn't have to exist, or they could have existed, but there was infinitely many solutions. So in this case, all these things, of course, will appear there, and it will get even more tricky, because as you can imagine, if the number of equations is not equal to the number of unknowns, there are some special cases, and that's essentially what we'll be talking about today. Okay. So the basic idea, our basic weapon is still the same. That the basic approach is to use Gaussian elimination to eliminate, to bring it to something that looks like the upper triangular matrix, right? When we are dealing with square matrices, the process was to apply Gaussian elimination until we got it to upper triangular matrix, right? So in general, rectangular systems will not be able always to apply, to get it to like a upper triangular matrix, like a beautiful upper triangle, right? If I was square, I could get it to a beautiful upper triangle, which looked like this. So there was exactly zeros here and exactly non-zero, potentially non-zeros over there, right? So let's see. I guess let's try an example. And let's first do the simple case where the b equals 0, okay? So we will start by considering homogeneous system. This is called a homogeneous system, where the right-hand side is 0. So let's take a look. So let's do some example. But first, I wanted you to just look at the homogeneous system. So in general, of course, I have some right-hand side, ax equals b, which can be non-zero. But it turns out it's very useful to first look at the case where the right-hand side is 0. It will turn out that it's okay. It will turn out that the general solution basically decomposes into two parts, and this being one part of that, the special solution, or solution of the homogeneous system. So the first thing you can notice about this, if I tell you just give me a solution, I think we discussed it last time, right? Can you immediately give me a solution to the system of linear equations? I think you can, right? Can someone else? Ax equals 0. Maybe I could, okay, let me first draw some pictures here just to give you a visual idea, which is what I always prefer. So we will be talking about, there are basically two cases, right? When we are talking about general matrices, they can either be fat and short. So that's if I anthropomorphize it. So this would be a fat and short matrix, sometimes some x vector equals b. So this is my x, this is my b. So this is the case where the matrix is more columns than rows. Anthropomorphal, something we call it short and fat. And there's also the tall and skinny matrix case, which looks like something like this. So in this case, we have too many equations and not enough variables Just want to get the dimensions right? So you know that the dimensions have to match. The number of columns here has to match the number of dimensions in X, and the number of rows here has to match the number of elements in B. Same thing here, right? Except that this is the case where we have more rows than columns. This is the case where we have more columns than rows. And both cases we will consider today, they are sort of closely related, as you will see, but they also have, obviously they are quite different, right? If you think about it, even before thinking about the solutions. Here we have not enough variables. Here we have like too many, right? Here we have not enough equations, right? So if you wanted, maybe you have heard these terms, this would be the case where the solution can be underdetermined. I don't have, so this is basically the equations tell me that I want something from my solution, right? And here I don't have enough of them. So it's underdetermined or ill-posed. Here it could easily be, doesn't have to by the way, but could easily be overdetermined, right? I have too many equations and not enough degrees of freedom to satisfy them all. All right? So yeah, let's go back to this. So we are starting with the case where the right-hand side is 0. So can you immediately give me a solution? Either way, right? It can be either this way or this way. Doesn't really matter. The trivial solution is always a solution, right? It's x equals 0, trivial, always solves it, right? Well, it turns out that, sure, that's an always solution, but what we are interested in here are the non-trivial solutions, right? Because the trivial solution doesn't even care what is in the matrix, right? So yeah, it is there. You can certainly argue that that's a perfectly valid solution, but what we care about is what are all the solutions, right? And then we will have to care about what exactly this matrix contains, right? Because the non-trivial solutions, the solutions that are not all zeros, they depend on the A matrix. So let's take a look, how can we find them? So as I said, we will so let's look at it on an example, and what we will do, we'll perform Gaussian elimination, okay? So let's take a rectangular matrix, so that would be the example of the fat and short matrix, right? The 3 by 4, so I have more columns than rows. And let's perform Gaussian elimination. So the first step is, so you should all remember Gaussian elimination, you all coded it up, right? So the first step is to eliminate this to 0. So I take the first row, multiply by -2, and I'll get an opportunity to check if I did it right. So this will give me -2 plus 2 is 0. That's good. The same thing here, -2 plus 2 is 0. Here it's -4 plus 8 is 4. -6 plus 10 is 4. Okay, everybody sees that? The right-hand side was 0, so nothing happened to it. That will stay 0. To eliminate the second row, I multiply to eliminate the third row, I multiply the first row by -3 now, and add it to the third one, okay? So it's -3 and 3 is 0, -3 and 3 is 0, so I was lucky that like 2 of them eliminated at the same time. That doesn't have to happen. The first one has to be eliminated, the second one, that was just a coincidence. -6 and 10 is 4, and -9 and 13 is 4. So that looks correct. So that was the first step of elimination. And the second step, so now I'm basically, okay, I guess if I was doing it more carefully, now I'd be looking at this submatrix, right? But here is 0 already, so I have nothing to eliminate. So already, we were lucky and already got eliminated for us. I guess that's just to make the example easier. So we can immediately move to this submatrix here, and we want to eliminate that. How do we eliminate it? Well, we take the second row, multiply by -1, right? And immediately see that this completely disappears. -4 and 4, -4 and 4 gives me zeros, okay? So this is what would be called the row echelon form. And I guess the way you can think about the row echelon form is sort of like the best thing you can do if you don't have a square matrix. So that's sort of the same sort of idea as upper triangular matrix, except that it's not exactly triangular, but instead has this staircase pattern. Okay, I'll show you a more comprehensive example in a second. Now we can keep eliminating to get it to even simpler form. So this would be, let me write it here, this would be the row echelon form. Row echelon form. And we can simplify it further, because what we can also do is eliminate this 2 here. Because all I need to do is to multiply this by -2, this -2, the second equation, and add it to the first one. Okay? That goes like the opposite way, but that's totally fine, right? I will still get an equivalent system of linear equations. So why don't I do that? So that means these are 0, so they don't matter. This I multiply by -2 and add it to 2, so that gives me 0. This is -2 and 3, so that gives me 1. So that's this 1 here. Everybody follows that? Is it too quick, too slow? You look happy, so that's fine. And this is what is called the reduced row echelon form. So this matrix is in a reduced row echelon form. And what means the reduced is that these elements, which are called pivot elements, so the leading non-zero in every row, here it's this one, so I look at every row and I find the first non-zero. Here it wouldn't even have to be ones, it could be arbitrary numbers. In the reduced one it will always be ones. So these are called pivots. And what happened in the reduced row echelon is that I made everything above the pivots 0, okay? So the pivots, that's just like in standard Gaussian elimination, right? Those are the numbers which you know you don't like them if they are too close to 0, right? Because then you would be dividing by too tiny number. And they are used to eliminate the entire column here to make their zeros. And what you can do, you can also eliminate upwards, so make zeros above the pivots. Now the last column here does not have any pivot because there is no non-zero element there. That's what happens when you are dealing with rectangular matrices, right? That's the nature of the beast. So in general, if I should explain what is row echelon, or let me just give you like a bigger example. You can find like a formal definition, but again, I sort of prefer to explain it by a drawing visually, because I think that will give you exactly the right idea. So the idea here is to have like a staircase sort of pattern. So these stars I'm drawing, that means these can be non-zero numbers, okay? And any matrix I can bring by performing Gaussian elimination to this form, to this staircase-like form, where I have a leading any number of zeros, and after that I have non-zeros, okay? And this matrix can end with as many rows full of zeros as I want. So let me do another one. There can be as many as you would like. And if I make this in a matrix, we say that this matrix is in a row echelon form. So notice the staircase type pattern here. So that's really the same idea as an upper triangular matrix, but because we are dealing with rectangular matrices, we just need to allow for the fact that we might need to skip, that we will not have the nice beautiful triangle. So that's the row echelon form. These elements here, these non-zeros, so the stars, that's sort of funny though, but let's be careful about it. The stars in general mean that there can be non-zeros, but they could also be zeros, okay? What are important are these pivot elements. So again, as I said, the pivot is the first non-zero in every row. So these are pivots. So in this case, these guys actually have to be non-zeros. These only are allowed to be non-zeros, but the pivots must be non-zero. Okay? And if I contrast it with the reduced row echelon form, so this is sort of like the mid step of it. This is what you get after just doing the plain vanilla Gaussian elimination. And I can further eliminate it to the reduced row echelon form, which will look for the same matrix, but look like this. So I can make this first pivot 1, because I said it must be non-zero, so I can just divide by it, right, and get it 1. And everywhere above the other pivots, I can just get their zeros, okay? So maybe, you know what, let me do it column by column. It will probably make a lot of sense. Did I get the right number? Yes, that's the right number. So here were zeros, right? So let me go column by column to explain this. So every column which has a pivot element can be brought to the form of a standard basis vectors. Okay, so everywhere zeros except for 1, 1. I think it's funny to talk about 1, 1, but that's what it is. So here also 0, 0, 1, 0, 0, 0. Here could be something arbitrary because this guy is not a pivot element. Okay, so if I'm bringing it to a reduced row echelon form, I don't know what exactly is going to be there. There can be zeros, there can be non-zeros. Here is a pivot element, so I can eliminate and get there a standard basis vector. And here will be whatever. There'll be something. Except that here I know the zeros will remain there. Okay? So the staircase pattern is still there, right? It's still the same type of idea. The pivot elements now became ones. So yeah, they are not arbitrary non-zeros, now they are ones. And everywhere above the pivot elements, I have zeros. Okay? And I think it should be obvious to you that you can always convert the row echelon to reduced row echelon, right? All I need to do is divide each row by the value of its pivot element, right? So that's an elementary row transformation, no problem. And then I can just add the multiples of the rows to the rows above them to zero that out, right? Notice that there are zeros here, so they will not mess with anything, so that's fine. They will not destroy what I did before, so in just one sweep I can eliminate above. That's the idea of the reduced row echelon form. Does it make sense? Great. So once we have done that, we are basically halfway through in solving. Well, there is still much more to it, but this is the key idea if you have a rectangular system of linear equations. So I guess we can continue with this example. So let's see if we can find some non-trivial solutions to this, right? We know the trivial one that works anytime. But the interesting question is we can find some non-trivial ones. So let's try to answer this question now. So we brought it to the reduced row echelon form. So I copied here. And here comes a little bit of terminology. So here the pivot elements are these guys. Okay, is that clear? The first non-zero in every row, those are the pivot elements. Okay. And the x in this case is 4-dimensional, right? So I can write the x as x1, x2, x3, and x4. Enough resolution there. You see it? Legible somewhat? Okay, I'm looking at those guys far back. So you know what that means? That means that basically this x1 applies to the first column, x2 to the third column, x3 to the third one, and x4 to the fourth one, right? You know how matrix vector multiplication, I assume, I hope you already have developed the center of your brain for matrix vector multiplication. So now the x's that correspond to the pivot elements, this is important, these will be called the pivot variables, okay? So in this case, it's the x1 and x3 because they correspond to the pivots, okay? These guys are the pivots, and they are in columns 1 and 3. So x1 and x3 are called pivot variables, okay? The remaining ones, oh, I guess it's also written here. The remaining ones, x2 and x4, they are called free variables, okay? Do you see where I'm going with this? Where I'm going with this is to get the full subspace of solutions to this homogeneous system of linear equations, right? So let's see. So the point is that for any choice, so the free variables are called free variables because I can choose x2 and x4 arbitrarily and compute x1 and x3 such that the system of linear equations is satisfied. Okay? So pick your favorite x2 and x4, like 17, 5, or whatever, right? And I can always compute you x1 and x3 such that all these equations will be satisfied, and therefore the original system, right? Because all the transformations we're making, and I just create an equivalent system of linear equations. Okay. So instead of just, well, let's see. Instead of just generating random x2s and x4s, we can give it some more order. So let me explain this here. I guess I don't want to give away the solution yet. You know what? Let me do it here. So I said that x2 and x4 are free. So it seems like a good idea if I look at the vector of x2 and x4 to plug their standard basis vectors. Okay, I guess in a little bit I will explain why that's a good idea, but intuitively it definitely sounds like a good idea. So the first choice would be that x2 will be 1 and x4 will be 0. Okay, so let's try to plug it in there and see what we will get. So from the second equation, we will get that x3 plus x4, which is 0, is 0. So that means that also x3 has to be 0. And from the first equation, we get that x1 plus x2. You know what? Let me write the whole thing to make baby steps here. So x4 we already know is 0. That's what we assumed here. The x3 is not even relevant because there was 0 here. x2 is 1, and x1 is what we need to find. So clearly, this means just, okay, let me do it really slowly. So this is x1 plus 1 equals 0. So that clearly means that x1 is minus 1, right? And we have our first non-trivial solution, right? So if I write it down, x1 is minus 1. So I start with minus 1. x2 is 1. x3 is 0. x4 is 0. All right? Ta-da! Here is our first non-trivial solution. Okay. What shall I call it? Well, I don't have to call it anything. Let's check that it solves our original system. I mean, it's sort of easy that it. Let's check that it solves this one. That's easy, right? So if I do a dot product of this row and this column, clearly I get 0, right? Trivially, because I'm only hitting zeros with non-zeros. And if I do this, if I do the dot product of the first row with this column, I get minus 1 plus 1. That's also 0, right? So that's indeed the correct solution to this. And because I was doing equivalent transformations, that's also the solution to the original system. Is that correct? Yes, it is correct. Because see, minus 1, 1. That's the all of them. Oops, all of them cancel out. All right. Well, there is another one hiding there, right? And the way I will get it is by setting x2 to 0 and x4 to 1. Okay, so let's see what happens if I do this. So from the third equation reads x3 plus x4 equals 0, right? I know that x4 is 1, so that means that x3 must be minus 1, right? Let's plug it into here. So that says that, okay, let me do it again slowly, otherwise I'll certainly make mistakes. So x1, I don't know. x2 is 0, that's what I assumed. x3 doesn't matter, and x4 is 1, right? So that means that x1 is minus 1 as well. So if I put them all together, put all these guys together, I guess, like this. So I will get, what will I get? I will get minus 1, that's x1. x2, I assumed that's what I picked, that was 0. x3, again, minus 1, and x4, 1. Okay. It's different than this, right? Quite clearly. And it also solves the system. Let's check it. If I multiply with the second row, I get minus 1 plus 1, that's 0. If I multiply with the first row, again, that's only minus 1 plus 1, it's also 0, okay? So another perfectly valid solution. And it turns out, and okay, so this is what I have here. Those are my solutions. Oh, by the way, what do you think would happen if I plug there x2 equals 0 and x4 equals 0. Huh? Yeah, I would get a trivial solution. But that's not what I'm interested in, right? So I plug in this, the standard basis vectors. Okay, so we can move on to the general solution. So so this basically takes care of the case where the right-hand side is 0. Okay, so what if the right-hand side is not 0? Or you know what? Let me first say that a general solution to the system I could write in the form of alpha minus 1, 1, 0, 0 plus beta minus 1, 0, minus 1, 1, where alpha and beta are arbitrary scalars. Okay? Because I can clearly, if I do linear combination of them, I still get 0. If I multiply them by something, I also still get 0, right? Is that obvious to everybody? Yeah?
Is that the form you want us to write it in? Write it down?
Sorry, come again?
Is that the form you want us to write it in when we answer it on the exam?
Yeah. I mean, you can write it whatever way you want. I mean, this is what makes sense to me. Yeah. There might be other notation. Yeah.
How about when x2 and x4 equals to 1? Both of them equals to 1.
What would you get? Well, but you would get some of the two, right?
Oh.
They form. We will get there. The solutions form a linear subspace. So if you just plugged in, well, you would get this, right? You would just sum them together. So you would get minus 2, 1, minus 1, 1. Indeed, x2 and x4 is 1, right? By knowing these two vectors, you can basically, that's the point, you can generate solution for any x2 and x4, right? I said, pick your favorite x2 and x4, I can give you a solution. Well, that's how, right? This is, all right, you know what? I can just put the x2 here and x4 here. That might be even better. And just say that x2, x4, or I can put for any x2 and x4 real numbers, scalars. Those are the free variables. This is what I multiply with, and I get a solution. Yep.
How do you know how many solutions you have?
So what is the, so we will get to it. So there is always infinitely many of them, right? As long as there is one, there is always infinitely many of them because you can multiply it by anything. So asking how many, we need to actually specify what how many means here. That means the dimension of the subspace. Okay, I will get to this later in the talk.
I know there are like infinitely many combinations, but how many actual vectors?
Correct. That's, you are asking what is the dimension of the null space of this matrix, what the dimension of the space of the solutions, right?
I'm asking like how many, like you have two of those vectors right there. Like how many of those are there? Like I know you can, there are like infinitely many combinations depending on what x2 and x4 you pick. But like how many are?
Yeah, because you're saying that for if I pick the different matrix, maybe I would get 3 here, right? Or 4, right. or any number, right? Yeah, so we will also get there. That has to do with the well, actually all the I don't think I can give you a quick answer now until I went through all of this. So, but you know how you could do it computationally, right? You just convert the matrix to reduced row echelon form and compute the number of pivots, right? The number of pivots, that's easy, right? For every row, you look at the first non-zero element, right? So here I have 2 pivots, right? So that tells you the number of columns minus number of pivots, that's the number of free variables, right? The number of free variables, that's the dimension in general, right? Don't worry, we will discuss this in more detail. There is more theory to it. There are subspaces and their dimensions, so it will make more sense once we have gone through it. But you know how would you code it up, right? You could just do it. You know how could you code up a MATLAB script that would give you the dimension of the space of solutions. Yep. Let's settle that question. Okay, if that's the case, then I would like to move to the general case where I have a non-zero right-hand side. So when I have some b on the right-hand side, where the b is non-zero, It turns out it's actually relatively simple. So the point here, at least the point of the slide, is that all I need is one particular solution, xp. So if I already give you one solution and I give you that xp already equals b, so I give you one solution, doesn't have to exist. We will discuss when it does exist. But let's assume for now that I gave you an xp, a particular solution, which solves it, and then the set of all possible solutions I can write like this. So the xk's here are my special solutions. So in this example, this would be the x1, I guess, and sort of poor notation, because here the x's mean the actual vectors of the solutions. But I think you got the idea. So the point here is that if I now apply a to xp plus the sum of alpha k xk, and I assume that the xk's are my individual special solutions, those are the vectors you were asking how many of them do I have, right? Those are the solutions to the homogeneous. So special solution means solution to the homogeneous system, okay? And if I do this, then obviously because everything is linear, then here I get just axp plus sum alpha k, let me just put it here, axk. This I assume that's b, I assume that already is a solution, and this is 0, right? So this is certainly b, so that means this completely characterizes all the solutions, okay? Similar sort of idea appears in differential equations and so on. The point being that this generates just 0 when transformed by A. So all my solutions I can get from one particular solutions by adding an arbitrary linear combination of the special solutions. Okay. Also, in the special case when you will get no free variables if you perform when you perform Gaussian elimination, transform it to reduced row echelon form, and you will see that there are no free variables. Well, that means that the solution is unique, right? I guess that would correspond to this k being 0. So this term in the sum doesn't appear, and you have just a single solution there. Okay, I will explain in a second, or actually maybe right now, how to find out if there is a solution, how to get the particular solution. Okay, let me do an example of that to give you a complete picture. Simple example will do, I think. So let's solve a system with non-zero right-hand side. So let's solve this system. Solve a system of linear equations, which looks like this: 1, 3, 0, 2, 0, 0, 1, 4, 1, 3, 1, 6. That's again a 3 by 4 system. It's about the right size to explain this. x1, x2, x3, x4 equals, and put this 1, 6, and 7. So that's a non-trivial right-hand side, right? So what would you suggest? So now the problem is that the right-hand side is non-zero, right? So can remember, did you do this for your project, the square system? So you know, if there was zeros, what I was just talking about, you would just perform Gaussian elimination on this matrix, right? And you can essentially apply the same idea here. So I guess one useful thing, if you are coding it up, or even if you are writing it on paper, you can create a thing which is called the augmented matrix, which basically, okay, if I call this A and this B, this is nothing but stacking the right-hand side as an extra column of the matrix. Okay, so in this case, the augmented matrix would be no big deal. Just basically copy the matrix and just put the 1, 6, 7, the right hand side, the B vector, as an additional column of the matrix, okay? And why I'm doing this is because then if I will run my Gaussian elimination, which I will run on the paper here because it's quite simple, if I'll run it, then I'm automatically applying the same operations to both the matrix and the right hand side, right? Because I just made it one matrix. So I guess it would be sort of cute if you were coding it, right? Then you don't have to code any special routines for this case. You would just create an augmented matrix and just call your standard Gaussian elimination code if you coded it up in a clever way. So let's try this. Let's run the Gaussian elimination to get it to reduced row echelon form. So here I don't have to, here I actually made the example simple, so here I don't have to do anything because this already has zeros here, right? But the third row I can eliminate, right? So I multiply the first row by -1 and add it to the last row. So I'll get 0, 0, this will be 1, this will be -2, and 6 is 4, and -1, and 7 is 6. Now you can see how the example is simple, because what is going to be in the next step of Gaussian elimination? Think about it before I write it down. So now I'm eliminating the last row, right? So what will I get there? What shall I write there? All zeros, that's exactly right. Because I just multiply the second row by -1, add it to the third row, it all disappears, which is beautiful. So if I should put it back into like the equation or system of linear equations form, now in the, oh, notice also that I also picked it so I don't have to do many computations on the paper, that this all of a sudden immediately, luckily, by coincidence, this already is the reduced row echelon, right? Because these are my pivots here, and above every pivot there are just zeros, okay? So this gives me this. So here will be my x1, x2, x3, x4. And the right hand side after the Gaussian elimination that became 1, 6, and 0. All right? And here's the thing. Here is how you can decide if the solution exists, and if it exists, then find what it is. Okay? Well, the key thing to this is the last row, the rows without pivot elements, right? So what is the last row saying? Nothing interesting, right? The last row saying is that 0 equals 0, right? So that basically it wouldn't even have to be there, right? I could just like cross it, make it just a 2x4 matrix and 2x1 right hand side, and it would be saying exactly the same thing, right? So that's essentially redundant, right? So here again, the free variables are x2 and x4, and the pivot variables are x1 and x3, just like in the previous example. And because here's the important thing. Because there was 0 on the right hand side, it means that I actually will have a solution in this case, okay? Because if you just forget about this, if we just really cross them away, then I'm back to a standard 2x4 case where I can pick anything for my free variables, and I can actually generate lots of solutions to this, okay? Now imagine there was not 0 here, okay? For example, let's see. Let's imagine I put there 8 here, okay? That means I would have 8 here instead. I would get 7 here because I just subtracted 1. So that means I would end up with 1 here, which means that I'll end up with 1 on the right hand side. What would happen in that case? In that case, I just cannot get it out, right? In this case, what does it say, the last equation after the elimination? What does it want? It wants no, so it wants that after I multiply these by zeros, I get 1. Well, that's impossible, right? That means no solution. Okay? So that's how you can decide if the solution exists or not. So if I had put here 8, I would end up with 1 here. The solution would not exist. So the solution exists if and only if these rows without any pivots correspond to 0 elements on the right hand side after the elimination. Okay. So let's assume it was the good case, so no 8 here, and here was just 0. So in this case, the solution exists, so I can be asking what it is, right? So let me compute it. So in this case, actually, so how do I find the solution? So I said x1 and x3 are pivot variables, right? These are my pivots. x3 and x4 are free variables. So I can just pick anything as the free variables and compute my solution, right? Here actually it turns out that I'm free to pick x2 equals x4 equals 0, because I cannot get, why does it work in this case? x2 and x4 equals 0. Before it was no good, right? Because I got a trivial solution, which I wasn't very interested in because it just works all the time. So what's the deal? I don't even have to be computing anything. Why x2 and x4 in this case actually is a good idea. Yeah, because this is not 0, right? So the trivial solution cannot be the solution, right? I must get something interesting here. So let's see what do I get. So the last equation tells me, so I put x 4 0. So the last equation tells me x3 plus 4x4 equals 6, right? x4 is 0, so wouldn't even have to be there. So it says that x3 is 6. Okay. And the first equation tells me what? It tells me that x1 plus 3x2 plus 2x4 equals 1. So, but x4 and x2 are 0, so they're out of it. So x1 is just 1. So here I have my particular solution, xp, to make it compatible with the previous slide. So x1 was 1, x2 0, x3 6, x4 0. Okay. Well, of course there are zeros here because I just picked x2 and x4 to be 0, but I have some non-zeros here, right? Like as I said, trivial solution at this time doesn't cut it, right? You have to actually compute something. Let's try if we got it right. Let's try if it, clearly solves this case, right? Because it is already in the reduced row echelon form, so that's easy. So you were previously asking how to write the entire set of solutions. So we need to look at the special solutions. So what are the special solutions in this case? It will be quick enough. Solutions, quick discussion. So for special solutions, again, I put x2 to 1, x4 to 0. Let's see, what do I get? So that means that x3 equals 0, right? So so now the right hand side is all zeros, okay? And I'm substituting for my free variables the standard basis vectors. So here it's 1 and 0. Are you with me? So that went from the second equation, and from the first equation, we tried to substitute it there already. So that will be x1 plus x2 is 1, so that's plus 3, 0, and x4, so that's nothing. So that means that x1 is minus 3, okay? So my first special solution, if I didn't make a mistake, is minus x3, that's x1, x2 is 1, x3 is 0, x4 is 0. All right. Let's try it. Plug it in there, I get 0. Plug it in here, I also get 0. So indeed, that's a special solution, okay? There will be another special solution because I have 2 free variables, right? So the second one I will get by getting the other basis vector like this. Ooh, sorry, this was supposed to be 1. That's the whole point. So what I'll get here? So I'll get x3 minus 4. So that means that x3 must be minus 4, right? x2 is 0, and from this equation I can compute that x1 0, plus 2, so that would be minus 2, right? X1 gives, and X1 goes to minus 2. By things like this, I would like you to be able to compute even in your head that something like this might appear in the midterm, so doing some simple computation. The numbers will not get complicated, but you should know basic arithmetics, I guess. The problem always is that it's easy to make mistake in it. Oh, it's almost guaranteed you will make a mistake in it. So you need to be able to recover from it. So this is my second special solution. So if I should write all possible solutions, so they form a set. They form an affine subspace, but we don't need to be that precise about it. So I guess you could write it like this. You could write it like 1, 0, 6, 0. I guess I should give some special points for a particularly creative way of writing the set of all solutions. But the whole point is to just find a particular solution and then linearly independent special solutions where x2 and x4 are arbitrary real numbers. Okay? Notice that if I plug for x2 and x4 zeros, I get exactly my particular solution. Nothing that special. Yep. Why did I need to find the xp? Because I don't have 0 right-hand side. If I had 0 right-hand side, then my xp essentially is the vector of all zeros, right? That's the trivial solution. Because my right-hand side is non-zero, the trivial there's no trivial solution, right? The zeros don't cut it. I need to find the particular one solution that gives me the proper right-hand side. Okay? It's easier than the other ones because I just plug there the free variables to zeros, right? Which sort of cancels out most computations, so that's kind of neat. And it works, just as I said before, because the trivial solution cannot solve it if the right-hand side is non-zero. Okay? Yeah. Yeah, Henning?
To find the particular solution, do you just always set your free variables?
Yes, I can always do that. Yes, because if my right-hand side is non-zero, right? But if my right-hand side is 0, I don't have to be finding any particular solution. I already know that the trivial solution is the particular solution. So indeed, yeah, this is just to deal with the case if your right-hand side is non-zero, which is generally the case, right? So the point here is that the set of all solutions splits to the particular solution, this xp, right? And then these special solutions, which I can have many of them. The number, again, is the number of columns minus the number of pivots. Don't worry, we'll look into that in more detail. Any other questions? Those are good questions. I guess you intuitively feel you will have to do this. Solving system of linear equations, which is correct. Okay, so let me summarize all that on this slide. So what are the cases for completely general systems? So the A can be rectangular, 0, whatever. B can be also anything. So I guess I could first split it into two cases, right? So the first is the solution, so no solution. There is no solution, it's done. And if their solution exists, then there are two possible subcases. Either I have some free variables, either I have at least one free variable, and with already one free variable, I can generate infinitely many solutions, right? Just by taking scalar multiples of the special solution. Now, if I have no free variables, 0 free variables, that's, by the way, the case of like an invertible square system, there is exactly one solution, okay? Now, let's formalize a little bit your questions about the numbers of solutions and so on. The useful concept here is what's called rank. You have probably already seen it. What is the rank of a matrix? or a system of linear equations, but you know that there is a one-to-one relationship between matrix and system of linear equations, right? So the rank is rank of a matrix is after you reduce it to row echelon form and you count the number of pivot elements, that's the rank. That's one definition of rank. That's the definition that makes sense for us at this point. But there can be other definitions too, but they will be equivalent. So that's how you can compute it, right? You know how to convert your matrix to reduced row echelon form. Just run Gaussian elimination, and just look at every row that gives you the pivots, right? Eventually, you might run into some 0 rows. So the 0 rows, they don't contribute any pivots, and that's the rank. Okay. So for a general rectangular matrix m by n, the first thing you can notice is the rank can be at most the smaller of m and n. Okay, because there can be only one pivot in each row or column. So let me maybe explain this a little bit better. So let's consider the two cases. So the first case is the short and fat matrix, right? The best that can happen to you, then what you get is the full number of pivots, right? That every row has a pivot, right? So this is the case, this is an m by n matrix. So this is m, this is n. So this is the case where n, when I have more columns than rows, right? And you see that the rank can be at most the number of rows, so the smaller one of them, okay? In the case when I have a tall and skinny matrix, then again, the best thing that can happen is that every column has a pivot, right? And here I necessarily have to run out of them, and the rest will be just zeros, okay? Simply because when I'm running the elimination, that after every pivot, below every pivot, I must have all zeros, right? So here are zeros everywhere, and here are also zeros. So there's just no room for any more pivot elements, right? So in this case, I have more rows than columns. Then m is greater than n. N is the smaller one. But again, the rank certainly can be more than n in this case, right? So in both cases, this is true. In both cases, the rank is at most the smaller size of the matrix, okay? Now, what can happen, these matrices are sometimes called rank deficient. What can happen is that you run out of the pivots earlier, right? That you run out of them like here, and it turns out that here, after your elimination, after you eliminated this row, there are some non-zeros potentially here, why not? But after you have eliminated this, you see, okay, there's all zeros down there, so we are done, right? There's nothing else we can eliminate. In this case, the rank will be less than m, strictly less than m, and such a matrix would be called rank deficient, okay? Similar situation can happen in the tall and skinny matrix. In the tall and skinny matrix, what can happen is that the pivots will look something like this. So here you would have the square part, in this case n by n part, and you run out of pivots already here. So here they wouldn't have to be zeros with different coefficients, but for this particle matrix they were zeros. So this would be again a rank deficient, this time tall and skinny matrix, okay? And there is a simple formula which says that the rank is the number of pivot variables. Oh, what is this saying? Oh, the number of pivot variables minus. No, this was actually correct. Sorry, I just didn't parse it correctly. So the rank, that's how we define the rank. Rank is the number of pivot variables. So trivially, the number of free variables is n minus r. In this case, when the matrix is m by n. Okay. because the pivot variables, the two types, the pivot variables and the free variables. So the remaining ones, the ones that are not pivot, they are the free ones. Okay. So in the special case of square matrices, this relates to what we talked about before about invertible matrices. So what does it mean for square matrices? It means that the matrix is invertible if and only if it has a full set of pivot elements, if it has n pivot elements, if it has rank n. Okay. So that if a matrix is invertible, that means that always has a unique solution, right? So if the right-hand side is 0, only the trivial solution is the end of the story. Okay? Oh yeah, and how the reduced row echelon form of an invertible matrix look like? Well, it must be the identity matrix, right? Because that's like the simplest example, or I guess the most basic example of a reduced row echelon form. Just the identity. Everything eliminates, just the identity remains. Okay. Oh, that's the simple case. Let's look at the cases of rectangular matrices. So here we are looking at a matrix which has more rows than columns. Okay, so that's the case of this tall and skinny matrix. Okay, so we have more rows than columns. And we say that the matrix has a full column rank if the rank is exactly the number of columns, right? We know that that's the maximum, right? The maximum rank is the minimum of m and n. In this case, the minimum is the n, right? So this is m, this is n. So if I have the square part here, so this would be my first n rows. The matrix is full rank if the rank is exactly n, if it's the maximum possible rank, okay? So that immediately implies that if I do the reduced row echelon form, then all rows are pivot rows. All rows have pivot elements there. So here I have actually nothing but identity matrix, right? The first n by n, so this is of course also n, so this is an n by n block of the matrix is the identity. And that also means that if I give it a non-zero right-hand side, if I get arbitrary right-hand side b, I'll have no solution or unique solution, because in this case, in the case of full column rank, there are no free variables. So it's either 0 or 1 solutions, okay? How do I tell, by the way, if I give you some x here? This is some x and some right-hand side. B. Again, how do I tell if this is the case of no solution or a unique solution? If the solution does or does not exist? I think I mentioned it. So here are all zeros, right? You write it there explicitly, right? They have to be zeros. Everything already been eliminated. Yep.
If b has a value below n is 0.
So I have to draw a line, right? So this is the first n elements here, and this is the remaining m minus n elements, right? So for the solution to exist, I must have zeros here, right? After I applied Gaussian elimination, right? So I apply Gaussian elimination on the matrix and the right-hand side. After it terminates, I need to look if these are zeros. If they're all zeros, I'm in luck, I have a solution. If there is something non-zero, I'm done, there is no solution, right? So in general, they don't have to be zeros, and that's the case of no solution, okay? And of course, if the right-hand side is 0, that means that the trivial solution is the only solution because it's unique. That's end of the story. So if I tell you I have full column rank matrix and I'm asking for a solution right hand side 0 for homogeneous solution, you can just like spit out trivial solution, done. If you know it has full column rank, so it's just not so easy to find out. That's what the rest will be about. So I guess the analogous case to this is full row rank. So in this case, actually the situation will be a little bit different. So here we are looking at the short and fat matrix. So if you don't like anthropomorphizing, then just say that it has more columns than rows, right? So this is m rows and columns. So I'm looking at the case where I have more columns than rows. Okay. So in this case, the row rank will be full if the rank is the number of rows, because that's the maximum number the rank can be. And just like before, this means that the reduced row echelon has the full number of pivots. So there are no 0 rows anywhere. And the interesting implication of this is that there is always a solution, right? Because again, okay, I don't have enough space here, so I'll put it a little bit higher. So this is my x here, just writing it so that the dimensions match. This is my b here, okay? No matter what my b is, you can always find a solution. Okay, because in this case, remember, the problem was that I had more equations than unknowns, and in case the right-hand side was not cooperating, I could get no solution, right? I could be just basically asking for too much, right? If I only have 10 knobs to tweak, and I'm asking them to satisfy 100 different things, that doesn't always have to happen, right? It only happens if I'm lucky, but not always, right? In this case, it's different because here I have more knobs than requirements, right? So I will always be able to satisfy any right-hand side, right? In fact, this even has bigger freedom because in general, so this m m is r, m is the rank, right? And n minus r, those are just the number of free variables, right? Number of columns minus number of pivots, that's the number of free variables. So I have n minus r free variables. So unless it's exactly unless the equality is being hit here, or equivalently if n is strictly greater than m, I will always have an infinite number of solutions because I will have at least one free variable, right? So unless m is equal to n, I always have an infinite number of solutions. So contrast these two cases. This is the case of overdetermining the solution, and this is the case when I am underdetermining, and I have more knobs than equations. Here is I have less knobs than equations. That's the idea. All right. So now what we are gonna do, we are gonna do similar type of exercise as we did in LU decomposition. So I will refer to what we talked about before. So let's recall that Gaussian elimination. There was this beautiful, I guess, formalism introduced by Alan Turing. I think it was introduced by him, or at least popularized by him. Is that the Gaussian elimination can be written using matrix multiplication by doing the elementary row operations. Let's talk first about row operations. So those are the basic operations in Gaussian elimination, right? Swapping two rows, multiplying row by a scalar, and most importantly, adding a multiple of one row to another row. That's how the elimination happens, right? And you remember from the square case that each of these operations can be encoded using a matrix multiplication with a special type of matrix called the elementary matrix, the EI matrix. After a little bit of head scratching, you should be able to write down what the matrices EI look like, right? I think we wrote some of them, if not all of them. And you might also remember that all of them were invertible. They are super sparse and invertible. Do you remember it from the square case? That's no big deal, right? Like a matrix that flips two rows is just a trivial permutation matrix. If I multiply a row by a scale, it's just a diagonal with one alpha, which multiplies the row. So that's easy. Now, by the way, what does it mean for EI? It must be square, right? Otherwise, I couldn't even be talking about invertibility, right? So, as a matter of fact, these elementary row operations are square matrices, okay? So if I want to write Gaussian elimination algebraically, I can just say that there is a sequence of elementary matrices, E1 to En, such that the original matrix gets reduced to a reduced row echelon form, or after I perform this multiplication, I get a reduced row echelon form. That's like how I kind of write algebraically a Gaussian elimination. So A here was the original matrix, all the E's are the elementary row operations, and R is the resulting row echelon form, reduced row echelon form. Non-reduced one, of course, that would look exactly the same. So as we know that all of these elementary matrices, they are easy to invert. In this case, the inverses are even sparse, right? So can you tell me what's going to be? So if I denote this entire thing as E, if I multiply them all together, I can do that, right? I'm going to multiply them all together to E. What's going to be in E inverse? I know how to invert every single one of them, right? So to invert the product, I just invert the order of the inverted matrices. En inverse, right? So that means I can concisely write it like this, that EA equals R, so the original matrix I can recover by doing this inversion of all the elementary row transformations. And the E is just multiplying them all together, okay? The same thing I can do also on columns, right? We talked about transposition. So essentially anything I can do on rows, I can equivalently do on columns. One way you can think about it, I can transpose the matrix, do what I was doing on rows, now it's happening on columns. Or here, equivalently, the elementary column operations, again, the same idea, right? Instead of replace rows from the previous slide with columns, you will get elementary column operations. So it means swapping two columns of a matrix, multiplying column by a scalar, and adding a multiple of one column to another. Again, exactly the same elementary transformation matrices, right? Except that if I'm dealing with a rectangle matrix, they will have a different dimension, right? If I have a matrix like this, which is M by N, then the row operation matrices, of course, have to be this square, M by N, and the elementary column operations have to be N by N. So I can multiply from the right. That's the only difference, that when I'm doing the column operations, I'm applying them on the right as opposed to on the left, as in the case of elementary row operations, right? Again, I'm referring to your center of the brain for matrix multiplication. So here, the same idea, multiply from the right, the sequence of elementary column transformations. And that brings me to, guess what? Reduced column echelon form, okay? So the same idea as reduced row echelon form, just transposed, right? So you can take the images I drew here before, somewhere, here, and transpose it, okay? Well, I guess I should do this, but it's not going to be visible. Yeah, I should really transpose it like this. I think you got the idea. I don't want to spend too much time because we are running out of time. But you got it, right? You could, it's just the transposition, really. So if I write it out, I get this. So the matrix gets transformed to a column echelon form by multiplying by E from the right. So I can equivalently write the original matrix by inverting this stack of transformations. So this, if I all multiply them together, I get some E. I know how to invert it, and I get some type of factorization of A. Okay? And what I want to get to is, it's probably what we will finish with today, that's the rank normal form. That's what you get. So that's how you can find a rank of arbitrary matrix. And basically the idea is to do both elementary row operations and elementary column operations. It turns out that if you do that, you can actually reduce the matrix to a form that is just a square identity and blocks of zeros. Okay? If you think about it, it absolutely makes sense, right? Because reduced row echelon brings it to this form, and then you can start doing elementary column transformations to annihilate everything here, and then you can do few column swaps to just get this to a identity matrix, right? So if you want, I can just, in this case it would be 4x4 identity, right? So it would be like this. I can even write you the zeros here if you would like, all zeros. So what was the dimension? There was a block of 3. This would be just all blocks of zeros, right? 0, 0, 0 everywhere. And the number of ones in this identity, that's exactly the rank of the matrix. So that's one way how you can compute the rank of the matrix. So here, notice I'm referring to the previous class, the general linear group. We just remind you that was the group of invertible matrices. And that means that all the individual row or column transformations, so the column ones I denote with a prime to differentiate them from the row transformation. So without prime it's row, with prime it's column. Doesn't really matter that the matrices have exactly the same structure, except that these are m by n and these are n by n. So these are, and they are all invertible. So as you know from the group theory, if I multiply them together, they stay invertible. So I can write that they are from GLM and GLN. Okay, so that's how we can compute the rank. So I think I'll need another whole lecture to get to the idea of the 4 fundamental subspaces of a matrix, which will hopefully put to rest all your questions you might still have about solving rectangular linear systems. Okay? So we will do that on Wednesday, unless you have some questions, of course. Okay, thank you.